Hello viewers and welcome to another episode of Space Science with Python. As promised, today we will continue with some data scientific insights with the database we created last time. So a small recap, we downloaded from the Minor Planet Center the most recent Comet data set. So orbital elements, the names and so on of all known comets. We put everything in a SQLite database. The SQLite database was quite small, I think only a few kilobytes or so, so I uploaded the database also on GitHub, and it should be available here under databases, comets, and then mpc_comets.db. And today, next time, and afterwards, we will have a data scientific, or let's say space scientific insight into this database. So what is the distribution of these orbital elements? What kind of scientific insights can we derive from it, and so on. So there are a lot of questions we will answer today, next time, and afterwards. And let's have a small recap of the database itself. So we have here the name of the comet, like for example the Hale-Bopp. We have something called the orbit type, which is C or P value, and it appears that this orbit type is also part of the name. So yeah, let's have a look at this maybe today. We have the perihelion, the semi-major axis, eccentricity, and other parameters. So you can easily compute, for example, the state vector of each comet. Yeah, you can use the spice function conics, where you put all the orbital elements in the function, and then you can compute the state vector of all these of all these comets for today or next week or whatsoever, and see where these comets are currently, where they are currently in the solar system. So most of them are probably very far away. So if you plan to create some 3D plot with matplotlib or even with plotly or with bokeh, please be aware that maybe you need to choose a logarithmic scale or so, and also try to plot the orbit of Pluto, for example, if you find the spice kernel. It is a kind of a challenging task, but you have all the tools I explained to you in the last couple of tutorial videos. So feel free to take this as a small task. Maybe in the future we will also create this kind of plot, but today we will exclusively focus on the database, its content, and see what kind of insights we can derive out of it. Again, today's session is again stored in GitHub, in the new folder, C and P-Comets. So yeah, the title will make sense later. First, we would like to have a small overview and understanding of the database and also its content. So let's start today, or let's start first with reading the database, reading its content, and see whether we understand what we see in the database. So I already wrote some libraries that we need to import, and now we need to establish a connection to the SQLite database. So we just write SQLite3 connect, and then we set a connection to the databases /comets /mpc comets.db. Yeah, this works perfect. And now we can use pandas to read the database and create a data frame out of it. So let's, for example, let's check the types, right? I told you we have this different types in there, so we can get some statistics about this type. So let's say we want to create a type statistics data frame where we just read the SQL. And what do we want to do? Well, we would like to select the orbit type, but I would also like to see what kind of orbit types are in there and how many. So I would like to count the number of orbit types from the table comets_main. But I need also to group by these, I need also to group by the orbit type. So what does it do? I perform a group by on the orbit type, so we have hopefully different letters. You saw already C and P. We will return the orbit type name, so C, P, or whatsoever. And the second column will contain the corresponding number of these orbit types, so the count. So we will see like we have 50 C types, 20 P types, and whatsoever. So maybe let's put it in another line to not exceed the line limit here. I think I put it to 80 or 100, I think. And we need to also give this the connection. So this worked. We can now, yeah, maybe put it in the same cell, print the data frame. And what do we have here? So we have in our database 4 types. The one is so-called the A type, and there are 13 in there. A type is like, yeah, let's say not, yeah, it's interesting because originally one thought it was a comet, but it's actually an asteroid. Yeah, maybe an asteroid with a, let's say, cometary orbit, but we will see in the future what this means. We have something called a C-type orbit. So C comets are comets that have are highly eccentric, and they have an orbital period of more than 200 years. So they come into the inner solar system, visit us, and then they leave for the next 200, 400 years. Yeah, so all orbits more than 200 years of orbital period. Then we have the P orbits. These are comets with a period of less than 200 years. And as far as I remember correctly, you have also to have, you need to observe it at least, yeah, I think how to say it, I think it was not only less than 200 years, but you need also to observe the comet already twice after passing the perihelion. So yeah, one orbit is not enough. You have to observe it twice. So also that I don't know, it's some kind of definition. And we have the I. We have only 2, so not a lot. We will take a look at this I type a little bit later, or just in a moment. There are also other types that are not in the database, and you won't be surprised because one is, for example, the D type. And I think if I recall it correctly, D type was observed, but one couldn't determine the orbital elements. So yeah, lost. You can say these are lost comets. Maybe something that was observed 800 years ago. You see it in some historic books. People describing it, and based on the date and also the position of the sky, you can determine the sky coordinates, and with all the known comets one cannot reproduce this one, and also the data is not sufficient enough to create an orbit. So these are orbits that are comets that are unknown, let's say. They disappeared. And the other one are the so-called I think these are basically it. I'm a little bit maybe confusing it because there were also the so-called X comets, and now it's maybe I'm confusing the D and the X type, but basically the D and X, they are not in there. They have unknown orbits, or orbits that cannot be reproduced or computed. So let's take a look at the I orbits. So we can simply create a new SQLite string. We say that we select all from Comet's main, where the orbit type equals I, and also we need to provide the connector. So let's see what we have here. We have 2 comets. One is Oumuamua and Borisov, and they have the Oumuamua has an eccentricity of 1.2 and Borisov of more than 3. And these 2 objects, as it started with Oumuamua 3 or 4 years ago, or 2 years, I think 3 years ago. And it was the first interstellar comet. So it was a comet that originated outside the solar system. So it's not from our let's say close vicinity. It came from another star system or so and had visited us. And the same thing applies also for Borisov. So the I stands for interstellar. So these are comets that observed us, visited us once, and then they left our solar system forever. And for now, we only know 2 comets. So there are, I think, there are also other objects with an eccentricity larger than 1, but this doesn't necessarily mean that they are of interstellar origin. They could have come also from our solar system. Then the orbital elements were altered by close approaches with, for example, Jupiter or Saturn or other gravitational effects or the outgassing of the comets. And that led also to maybe an eccentricity larger than 1. But for in these two cases, we are pretty sure that they are not of solar system origin, let's say. They are really of interstellar origin. So let's take a look today at the 2 particular classes, the C and the P type, because we have a lot of these objects in there and they're also very interesting. And let's see what the dynamical or physical properties are, how they differentiate. I mean, I already said P-type, orbital period less than 200 years, C-type more than 200 years. It's a little bit like an artificial limit or border, but we will see that also the orbital elements, they differ. They really differ, and it's not something so they don't have dynamical properties in common. So let's take a look at this. We will first select some information for the P-type comets. So P-type DF, select Aphelion in AU and the inclination in degrees from Comet's main. You may ask, why am I taking only this information first? Well, of course, the coding tutorial orientates a little bit on I already prepared some code, of course, and I don't want to do now some extensive exploration, extracting everything, plotting everything. You can do this, for example, with Seaborn, but then you need to recreate your container, and then you can create miscellaneous plots. But here, I want to lead you a little bit into the, let's say, right direction. Now the limit, again, exceeds a little bit. So let's make a line break. Put it like this. So this is like for our P-type, and then we can simply copy paste it and use it for C-type as well. So C-type, and this is a C. And I think this should work. No, it doesn't. No such column orbits. It's called orbit type. It's not orbits. Okay, this should work. Perfect. What we can do now, for example, before we plot anything, we can simply use some descriptive functions. So pandas has a function called describe, and describe simply computes the number of counts, the mean, the standard deviation, the minimum value, the maximum value, the median, and the 50% range, and so on. So let's take a look at this. You see also I'm not using the print command. I'm just printing the command, the describe function here. Also here on the top, you saw that I didn't wrote print read SQL, because then VS Code or Jupyter is now formatting my table, and then I can scroll a little bit, and this looks a little bit fancier. So what do we have here for the P-type comet? We see we have 662 objects. The mean aphelion, so the far away, the sun farthest point is 7.7 AU. The the median is around 6, and the inclination you see here is mean is 16 degrees, the median is at 11 degrees. Okay, so let's take the median, and 50% around this median are between 7 and around 19 degrees. So yeah, one can say a lot of these comets of P-type are very close to the ecliptic plane. So they are orbiting around the sun, closely to the ecliptic plane, of course, a little bit scattered, more than our planets apparently. And we have also here some objects, or at least one retrograde comet, so with 170 degrees. Now we can do the same thing also with the C-type. And I would say let's focus also here on objects that are revolve, so they're on the bound orbit. So yeah, I will just limit it a little bit here. Yeah, so C-types, we have 255 C-types. And now I want to limit this by with the using the eccentricity. So I think the name was eccentricity should be smaller than 1. So we have only closed orbits. Let's print this one. And eccentricity. Did I do a mistake? I don't know. I mean, I don't see it now apparently. Just give me one moment. Let's take a look at the C-type DF first. I think I forgot, yeah. I forgot to extract the eccentricity, of course. Eccentricity. Yeah, that was the mistake. So now this should work. Yeah. Let's take a look at the statistics of the C-type. Well, the mean or the median is at 500 AU. So these comets, they are flying away. So they are, yeah, they reach, let's say, outer space where it's very dark and cold. And also the inclination, you can see the median is not here as in for P-type comets, 11 degrees. Here for C-types, we have a median of 80 degrees. And 50% are between 40 and 122 degrees. So yeah, it appears that these objects, they are not, let's say, orbiting the sun closely to the ecliptic. It appears more scattered, so really severely scattered. I mean, a lot of these objects are even on retrograde orbits. I think we have to create some plots to get a better understanding of this data here. So you see also here the eccentricity, for example, it's extremely close to 1, so very eccentric orbits. And also of C-types, we have 167 comets that have an eccentricity smaller than 1. And we had, if you remember, in total 255. So around 90 comets of C-type have an eccentricity larger than 1. Again, that doesn't mean they are interstellar. It means they are just on an outbound orbit of also solar. Their origin is the solar system. And of course, we do not have here any covariance metrics for the eccentricity, for the inclination and so on. So it means that even objects with an eccentricity larger than 1, they can also have a solution space that is smaller than 1. So, for example, the eccentricity has a probability of, let's say, 60% being larger than 1 and 40% being smaller than 1, right? I mean, there's a lot of uncertainties depending on the accuracy of the measurements of the observations and so on. So let's plot the data. Let's plot the data of the aphelion and the inclination to see the difference between the P-type and the C-type objects. So, of course, I prepared a little bit code already. First of all, I would like to use the dark mode. Yeah, so dark background as always. Space is dark, so the plots need to be dark as well. And also, yeah, we should also, I mean, for me, Matplotlib always sets a very small font size. I don't like it. It's sometimes really difficult to read. So per default, I always increase the font size. I put it mostly to 14 or 15. Some people like it a little bit smaller, let's say, but yeah, I'd want to read it without getting a headache. So let's increase it. It's up to you. We create subplots with a figure size, say, of 12,8. And now we can create a scatter plot. So the first scatter plot will contain the p-type, and the other one will contain the c-type. And yeah, I will also only consider the objects with an eccentricity of smaller than 1 for the c-type comets. So let's take first the p-type. So this should be like this. P-type df. So let's plot the Aphelion AU versus the inclination. The inclination is given in degrees, so no need to convert it. Inclination in degrees. Thank you, autocompletion. Appreciate that. And of course, we want to differentiate between P and C type. So let's set a marker for the P type. Marker, maybe, I don't know, dots. And then we can also set a color. Yeah, my favorite color is always orange. So let's take orange. And there will be a lot of dots. So already checked out, alpha of 10% is quite good. And we also put here a label where we just write p-type. It's explanatory, I think, hopefully. And now we can do the same thing for the c-type. And the c-type, first let's change here and here. We change also the marker to, let's take triangles. And we will use blue color. And of course, we will use the c-type. And since we have less objects here, let's increase the alpha value. And of course, important, we have to filter by the eccentricity. Now, small funny feature of VS Code, I don't know, for Windows, it's probably the Alt button. So I don't know, the button, the key on the right from the control. For me, it's the key left from the command. If you press it, and then you make like a left click, you have a multi-cursor. So you see here now 2 cursors blinking, and now I can write the filtering without any copy paste. So now let me write it. You see, I just do it immediately. I write the log command. Oh, there's no need for log. I just want to filter. So let's see, C type df, eccentricity smaller than 1. So this is pretty cool with the multi-cursor. If you want to write redundant columns, it's pretty nice. Yeah, shall we have a first look at the graph? I mean, then we can improve it a little bit before we interpret it. So let's see. Okay, so what do we have here? We have here the aphelion on the x-axis and the inclination on the y-axis, and this looks really dense and a lot of points are very far away. So I think it would be sufficient to change our scale from linear to a logarithmic scale. So log, let's replot it. This looks a little bit better. So this may make sense. Since we are talking about the inclination values, we can set a limit between 0 and 180 degrees. So Matplotlib doesn't need to decide it for us. We would also like to add a grid, because also if you later want to publish a paper or something, a grid is always something, a good support for the eye. And let's use the dashed one. This looks a little bit ugly, so we can adjust the alpha, let's say 0.2. Well, this is quite nice, so I think this would be quite helpful. And of course, we need to set a title and of course the labels as well. So let's set a title. You always need X labels and Y labels. I mean, for you, you say, I know it now, it's trivial and so on. But if you are working, for example, on your bachelor thesis, master thesis, or for fun, you're programming, it's really difficult maybe a week later to understand what you did. So really always write documentations. You have seen that also the code I'm uploading contains a lot of comments. Maybe it's sometimes a little bit overkill. Yeah, I hope you will not think, oh God, this is way too much. But believe me, it's really helpful in the long run if you comment and write everything down, especially in Jupyter notebooks, because Jupyter notebooks tend to be chaotic sometimes. So it's just my experience. So always take some time to write a documentation. Also, if you write, compute or create libraries, always write a documentation. Create a CI/CD pipeline that forces you to write a documentation. This is also how most of the open source libraries work out there, especially with a lot of contributors. And while I'm talking, I should maybe also concentrate a little bit on what I'm writing. So let's see. Comets with an eccentricity smaller than 1. We have here the aphelion in AU, the inclination in degrees. There is no typo, hopefully. I don't think so. So we have some text here. Now we can also add a legend, x.legend. I like the fancy box equals true. Location, I think upper right or upper left. Let's take the upper left. So I think we will not cover any data points. The p-type is a little bit difficult to see, but we will see how we can change that. We can also set the frame alpha to 1. And now this is also quite nice. Sometimes if you have a scatter plot, you want to adjust the alpha values, the transparency, because if I would set an transparency of 1, this would be just a huge orange blob. I mean, we can just try it out. Let's see what happens. And of course, this for loop is not finished yet. And you see, this looks really disgusting. I mean, you can create a histogram, 2-dimensional histogram plot or density plot to get a better feeling. But for a quick and dirty analysis, you would like to get a feeling of the density. So this is the reason why we are setting an alpha value of, let's say, not 10. This doesn't work. 0.1, because points where they are overlapping, you see it's, let's say, brighter than more sparse regions. But the point is, however, that in the legend we have the same alpha value apply. So you see the p-type comet, it's not really visible. So how can we change this? Well, this is quite nice in matplotlib. We have created a for loop where we take the legend box and we are iterating through the legend handles. And for each legend handle, we can say, okay, you know what? We set an alpha of 1. Yeah, so it doesn't matter what kind of alpha value we set here. Here we have bright spots. And I think this is quite helpful. If you disagree, please leave a comment, but I think this looks, I mean, one understands this, right? You see p-type orange, c-type triangle in blue. Also, you may ask, why setting triangles and not maybe dots? Well, the point is, if you if you publish a paper, some journals, submitting, let's say, color images costs more money. And also other people, I mean, of course, everybody's working digitally and so on. You read maybe papers on your screen or on your tablet or whatsoever. But some people still like to print stuff out. And some people don't have a color printer, only a black and white one. And then it's quite helpful to have, to distinguish between data points, not only from the from color, but also from the shape. And some people are also maybe color blind, or it's difficult for them to distinguish between different colors, especially if you have a lot of different colors, then it's getting difficult for them to see the difference. So try to create plots that can be that are understandable and that can be interpreted by everyone. And this is kind of an art, I would say, but yeah. We can interpret the graph we just see here. So what do we see? Well, it appears that the P-type and the C-type comets, they are really different populations. I mean, we see here that the P-types, they are concentrating in the solar system, so up to, I would say, 10 AU. And here's a blob, so the sun farthest point is at around 1, 2, 3, 4 or 5 AU, which you can see here. We'll see not in the next one, but in the second video after this one, the reason why this blob is here so bright, why we have so many P-type comets in this region. And the other thing is the C-types, you see, they are really scattered. So there is no actually, we don't see any preferent region or so. There is, we have every Aphelion value between 10 and, I don't know, 10,000, 10,000 and so on. And also the inclination varies between 0 and 180. So this looks really random, I would say. And I would suggest that we create a distribution of the inclination of the C-type comets to see whether we see any preference here, also maybe for the P-type comets. So we will take a deeper look into the inclination distribution next time, where we will also cover something which is called kernel density estimation. So it's not only about histograms, but also about this method called KDE. Maybe some of you, especially the data scientists, know this already, but I will also cover this next time a little bit more in detail. So we will create a figure not only with a histogram, but also with this KDE method. And then next time we will also understand what is the origin of the C-type comets. And after this, we will cover the P-type comets. And then we know where they originate from, how they are related with our with maybe planets of our solar system, where they come from, and what are the underlying hypotheses for especially the C-types. Of course, you can go to Wikipedia whatsoever, check the reason, what is the difference between P and C-type, and see what are the current scientific explanations. Of course, there are already explanations, and we have a good understanding. But here I would really like to show you the interpretation with the data, with using suitable plots to see what is the reason for the data, for the scatter plots we see. So for the distribution, the population of the comets. And that's a nice thing about this simple data engineering task we are performing and plotting. We can really generate scientific insight out of it. So I hope you enjoyed today's video and you learned also a little bit how to improve a little bit plotting and to make it more accessible for everyone. And next time we will cover the C-type comets, and until then, take care and see you next time.